Hello, today we shall be talking about Ludwig Boltzmann. He is best remembered as the father of statistical mechanics, and this is basically a field of physics that is invented to explain the laws of thermodynamics. Now, thermodynamics was actually the laws were actually penned down a long time back by people like Cantrop, Clausius, and Kelvin. But the interesting thing is that nobody really had an explanation for these laws. They were simply found out by empirical means. That means through experimentation. Now, this statistical mechanics explain the second law extremely well. What is the second law? The second law states that entropy increases to a maximum in the universe. Sounds like quite a blown statement, doesn't it? So, what is entropy? Well, in most popular places, it's described as the amount of disorder in a closed system. And a closed system is nothing but a system that is not affected by its surroundings. So, the universe is actually quite a good example of a closed system because, it consists of everything anyway. There's nothing outside the universe. So, let's explain entropy in a different and more correct manner, because disorder can mean literally anything, right? Disorder to you might mean order to me. It's quite a subjective word. So what exactly is entropy? It can best be explained using the concept of macro states and micro states. And to explain what that means, let's use an example. Let's say that I have this closed container, okay, a closed system, and I fill one side of it with oxygen molecules. Okay, and the other side I'm going to fill it up with nitrogen molecules. So I, as an observer, know that on one half I've got oxygen molecules and on the other half I've got nitrogen molecules. So I know that the macro state of this system, as being a macro observer, I know that one half is filled with some particular gas, the other half is filled with a particular gas. However, if I went around naming the individual molecules, let's say I assign this molecule a number 1, like we assign humans names the same way. I assign this as number 2, I assign this molecule as number 3, and this is number 4, and so on and so forth. Then I cannot really figure out whether this molecule is here at time is equal to 1 second, or this molecule is over here at time is equal to 2 seconds. They might have swapped, right? So I, as the observer, know that this is the macro situation, but I cannot pinpoint to each molecule individually and say where that molecule is. Now, the exact positioning of the molecules, 1 being there, 2 being there, 3 being there, 5 being here, 6 being there, that is known as the microstate. Something that the observer cannot really know about the system. So what that means is that in this particular macro state, I can have many microstates. In fact, billions of microstates, because there are billions of molecules within this configuration of half of them here and half of the other molecules on the other side. That is what entropy is basically all about. It is directly linked to the number of probable microstates within a given macro state. But what does the statement mean that entropy will reach to a maximum? That simply means that entropy will increase over time. And how does that happen? Now, over time, we know that diffusion will take place between these two gases, right? So if I've got the nitrogen molecules, they'll be all over the place. They won't be restricted to one side. So let's say this happened in time is equal to 0 seconds, and now we're saying time is equal to, 100 seconds. Okay? So now the nitrogen molecules are everywhere, and so are the oxygen molecules. They're everywhere. Now, if you noticed, over here, the oxygen molecules are only in a specific area, and only in a limited area, this much. And so are the nitrogen molecules in this much area. But now they fill up the entire space. So in this macro state where everything is filled by everything else, there are a number of microstates, because this number 1 molecule and this number 2 molecule can be literally in the entire box. So there are way more permutation and combinations, and hence that's what Ludwig Boltzmann was trying to prove. He used this concept of atoms to explain entropy and the second law of thermodynamics. Wait, what did I mean by this statement? He used this explanation of atoms. Yes, that's right. I said this explanation of atoms because at that time, in the German-speaking world, they had not entirely accepted the concept of atoms and the kinetic theory in general. And that is what statistical mechanics was built upon. It was built upon the assumption of atoms. So, and the explanation of thermodynamics simplifies so much using atoms and molecules in the kinetic theory in general. But his colleagues really didn't believe him, and they felt that the theory of atoms and statistical mechanics was just a simple way to explain thermodynamics. That there was a more rigorous proof, because they believed that solids and objects were continuous, that they weren't made of tiny little particles. In fact, it's quite sad that, it's said that he died of depression because nobody took him seriously in the German world. And he committed suicide in 1906. And interestingly, a few years afterwards, there were experiments done on colloidal theory, specifically the Brownian movement, that proved that atoms existed. And Einstein wrote a paper, his thesis in 1909, about explaining the Brownian theory and really proving once and for all that atoms did exist. So it's kind of sad that nobody really recognized statistical mechanics back then, and this beautiful explanation of the second law of thermodynamics and the explanation of how entropy can increase over time. Now, this entire concept of thermodynamics, to really give you a sense of what it means, thermodynamics also states, so what cannot happen as a result is that this system cannot go back to being in its original state. The oxygen molecules in one place and the nitrogen molecules in the other place. Now, if you think about it commonsensically, so this is t is equal to 200 seconds. Like if you think about it, these molecules could, in the random motion, go back into the original position where oxygen is to one side, nitrogen is to the other side. And I mean, it does not really contradict Newton's laws. However, the probability of that happening is really less. And that is the essence of this field of physics. That it's all about the probability in specific atoms, in breaking down matter to its base particles and then working out the probabilities amongst them. And hence the explanation of the second law of thermodynamics. Anyway, so Boltzmann also laid down his formula for entropy, which is over here. So this is the number of microstates for a particular macrostate. This is the final entropy that it's calculated, and this is the Boltzmann constant. Obviously, nobody took him seriously up till now. In fact, now his grave has this formula engraved on top of it. And there's this one last thing I'd like to talk about his work. That is the Boltzmann distribution. Now, interestingly, Maxwell, who was Scottish and I think lived before Boltzmann, had come up with a similar theory. But they never worked in collaboration, and hence it is known as the Maxwell-Boltzmann distribution. Now, Boltzmann, as I said, was a great believer in the atomic theory in general. And he believed that gases, and he wanted to explain this through gases. So he believed that if I have a container with gas molecules with a temperature of, say, 400 Kelvin, that does not specifically mean that all the molecules within this gas are moving with that amount of energy of 400 Kelvin. He believed that there was a graph, that there was a distribution, that there was a distribution between the number of molecules and the energy state. So he drew a graph, a distribution like this, something that was steep in the beginning and then panned out later. I've not drawn it well, but this should be, this should not be so steep. It should be like that. So what that means is that not every particle is at the energy state of 400. Okay? So most of the particles will be at 400 Kelvin. This is the Maxwell-Boltzmann distribution. This also means that, let's say the temperature was 200 Kelvin, then the energy at the maximum number of molecules will be lesser, around here maybe. So the distribution will look somewhat like this. Now if you notice, the peak has increased. Why this increase? Because the area under both the curves needs to be the same. Because even if I change the temperature, the amount of molecules will remain the same. But at the same time, the energy has to decrease. Hence, this new curve is narrower and taller than the original curve. Now, if the temperature was 600 Kelvin, my graph would look something like this. This is broader but shorter. So this is the Maxwell-Boltzmann distribution. It's the last thing I wanted to talk about him. So I hope you've got a fair amount of idea what he did. By the way, all this work of his is extremely simplified. He carried out all of this in 40 years. And there's much more to his work. And at the end of the day, he's called a father of some field. I mean, how do you even do that? That's amazing. Anyway, so I hope you enjoyed this video. And thanks and subscribe.